Okay, so I'm Jane Atha with Department of Fish and Wildlife, and this project is really kind of a first attempt to integrate climate change into the way that the Department of Fish and Wildlife designs and permits culverts. So, being the Department of Fish and Wildlife, we are concerned with fish passage, and we have a serious culvert issue in the state of Washington. Just a few of many potential fish barriers that we can have in and around culverts would be excessive water surface drop, a perched inlet or outlet in a culvert, velocity barriers. A little guy especially, isn't going to make its way up a fast-flowing culvert. We have shallow water depths that are also fish passage barriers, and they kind of go on and on. Excessive aggradation upstream of some of these pipes. So the scope of the issue, statewide, we have 14,000 known culvert barriers in our database, but this is just what we know. They're estimated to be upwards of 35,000 barriers statewide in the state. So it's a big issue. And our role as being part of this issue is that we provide design guidance for most entities among the states. We also permit and oversee the installation of culverts, and we also design culverts on our own lands and with partnerships. So providing fish passage is a big part of our mission. It is the only proven salmon restoration practice. We have thousands of culverts, as I mentioned. We're only going to have an increase in culverts. We're continuing to have more roads built every year. Some of the reasons for fish passage failure are currently unknown. We are working hard to try and figure out what constitutes failure. And the culvert lifespan is 30 and up to 100 years. We'd really like new culverts to last at least 100 years. And we definitely, as we've learned from the two previous talks, have hydrologic projections increasing within that culvert lifespan. So we want our culverts to be resilient. And currently, we're not considering climate change with culverts. So, our challenge, we are going to have higher and lower stream flows, as we've heard. Culverts that are under-designed are going to fail to pass fish, and we'll learn a little bit more about why that happens. We're not addressing climate change currently, and this current project is really a first step for us as an agency to really look into climate change. So with that, I'm going to tell you a little bit about how the Department of Fish and Wildlife actually provides guidance on culvert design and how we like to approach culvert design for fish passage in particular. So we use a geomorphic approach to culvert design. And what that really means is that we want to have as minimal of an impact on the natural stream processes upstream and downstream and through the culvert, with the idea that we are supporting and maintaining habitat for fish. And we have a strong emphasis on the continuity of stream processes. We want the sediment to move through. We want debris to be able to move through as well. So we want robust stream simulation culverts. And this is just another look at a typical longitudinal profile and how we subdivide a stream from the headwaters up on the left down to the outlet of a stream into basic geomorphic classifications. And you can see, where most of our fish passage concerns are along this longitudinal profile, and this also corresponds with where most of our culverts are located. So again, we like to design culverts that look at where are we along the stream profile, what's our slope, how much material, what kind of bed material sizing do we have up and downstream of that pipe. And one of the key metrics that DFW uses statewide is bankful width. And the bankful width measurement is basically the width of a stream from the regular every other year Q2 flow. So just where the flood waters are about to overtop the bank It's that width measurement that we use for our culvert design. So you can see here we permit primarily two types of culverts. The no-slope culvert on the left is for smaller streams, 10 feet and under. So again, we're looking at fairly small streams here, and we want that pipe to be at least bankful width wide. And these are on fairly flat stream reaches. And stream simulation culverts are for culverts of varying slope, up to 15 feet wide. Anything greater than 15 feet, you're going to want to put a bridge in anyway. So we have this safety factor that was kind of brought up earlier of this 1.2 times bankful width plus 2 feet. And this gives quite a bit of room for the stream to migrate and can very much accommodate these extreme flood flows. So what does this mean for us when we're looking at hydrologic data? And how do we translate into how we actually design culverts at the operational level, which is through a channel form measurement, a width in meters? So it turns out that we can do that. So we've got this idea in geomorphology. It's been around for 50 plus years of downstream hydraulic geometry, and it basically is simply saying that is discharge increases, our channel characteristics are going to adjust proportionally with that increase in discharge. As Rhonda pointed out, area can also be a surrogate for discharge, but we happen to have discharge data via SIG, so we're excited about that. And how we actually took that data and got it where we wanted to go. We took the wonderful data from the Climate Impacts Group, the GCM data that was downscaled to the Pacific Northwest and run through VIC, and we used that grid cell resolution, 1/16th degree resolution data. And it's important to note that this data came to us at the daily mean resolution, and we had to work with that to get to our bankful flow measurement that we can in turn translate into our key metric, which is bankful width. So DFW took the stream flow and determined bankful flows from that daily mean data. And I won't go into how exactly we did that. It involved lots of programming. And we were able to, in turn, take those bankful flows and translate those into bankful widths. So how we did that is a set of very useful regressions. Basically, again, this idea of downstream hydraulic geometry asserts that channel variables such as width, velocity, depth vary as a power function with discharge. So a fairly simple regression equation, power equation, and we're looking at the discharge. What we need is the bankful discharge, which in the state of Washington is the 1.2 or 1.5 flow. So this is the flow that's going to happen pretty regularly, right? So once every couple years or so. And we can determine those coefficients empirically with data taken out in the field, and that is what the work of Janine Castro and Phil Jackson did back in 2001 for the Pacific Northwest, and they got R-squares of 0.76 to 0.87, which are pretty darn good, for the region, and we felt comfortable using those regressions to, again, translate our bankful flow into bankful width estimates. So these bankful flows do vary by ecoregion, so we had to subdivide our data by ecoregion to get, again, just a more finely tuned bankful flow that we felt confident to make future projections with. And we did keep it at the 1/16th degree grid cell level, and we did this for all 5,270 grid cells in the state of Washington. Just to kind of ensure that we were looking at the right resolution, we determined that we wanted to stay at this 1/16th grid cell. As you can see, if you apply those regression equations to a 15-foot stream for each of these ecoregions, it coincides with the grid cell. So we didn't, spatially aggregate it up to the HUC-12 level, for example. So we took the VIC data, which they have a simulated historical period of record, and that period of record is from 1915 to 2006. We took the mean daily flow and determined the bankful flow, and in then turn got the bankful width for that historical period of record that was simulated through VIC. And then we used the A1B scenario, which is the 10 ensemble models for 3 different time frames, and did the same thing. Got the mean daily flow, translated that to the bankful flow, and found out bankful width. So SIG provided us with the mean daily flows, and then us at DOW translated that into that bankful width metric that we really use for our culvert design process. So with those historical and future bankful flows, we then determined a percent change. So how is that width going to change in time? And this is actually something that we can take out and use at a culvert site. So, I didn't have anything else there. And that's why we are looking at percent change rather than the actual number in meters itself, because we wanted to be able to, if you go out to a site, measure it, it's 5 feet, apply your percent change, see what it might look like and how your design might change. So just to give you a few results on what we saw with changes in bankful width. Mean percent change in bankful width for the 2030 to the 2059 scenario, you can see anywhere from a decrease in bankful width projected in the Columbia Plateau area, and of course increases in the higher elevations of the Cascades and the Olympics. This is good that it's not different from what previous researchers have found. And that variability really expands once we get into that 2070 to 2099 scenario. And again, we want our culverts to last this long. So this was definitely important news for us. And you can see, channels getting, having decreases in bankful width, and then even more of an increase, up to 38% change in bankful width. So then we were interested in seeing, okay, so what are the implications of this for how we design culverts? And one way that we looked at this was, okay, so we've got 10 models within this A1B scenario. And how many of those models across the state are going to tell us that our no-slope culverts, which again are designed for that bankful width, are going to be too narrow? So this reflects the number of models per grid cell that are telling us that the culvert's going to be too narrow to pass fish. And the red are saying that all 10 models are giving us a likelihood that it's going to be too narrow. And here is just another snapshot from that 2070 to 2099 scenario. Okay, so moving on from that, I had to step out of the science realm and think, how are we going to incorporate this information realistically at an agency level? So one thing we as an agency consider very often is risk. So the probability of loss or damage, and for our agency, fish passage failure, and the magnitude that that might occur. And risk being that magnitude times probability. So perhaps we can frame it this way. If we look at our mean percent change in bankful width on the y-axis, and then our number of models that are predicting an increase in that change, each red dot is a grid cell, so this is all 5,000 plus grid cells for Washington. We can perhaps delineate an area of those grid cells that have perhaps more than a 10% change or increase in bankful width, and maybe more than half of the models are saying it's going to increase. And within that area in yellow, which is arbitrarily drawn, maybe that's the actionable risk where we might actually need to consider component change in our design. So one case study a trib of the Tucannon River. This is in the Blue Mountains. This is a very interesting grid cell. It's got 10 models, 10 bankful width projections. So we have a bankful width projection per each model. And we can look at it perhaps this way as part of a cumulative distribution. So our first model is telling us that we have a negative 2.5% change. I like the mood lighting. So we've got negative change. The second model is saying we've got 1.6% change, and you can see we're kind of building our staircase here. And then onwards and upwards to where our fifth model is 16.2%. And then on to our 10th model, which is saying we're actually going to have a 46% increase in change. Now, I really want to stress that this is a very extreme grid cell. In fact, I think this is the most extreme grid cell that we found. There isn't typically that much variability among the grid cells in the state, or among the models. So if we look at that, so each of our vertical lines is a model prediction. And we've got 9 out of 10 models telling us that we're going to have a percent increase in bankful width. We have a range of percent change from negative 2.3 to upwards of 46%. And our mean change here is 22%. So that is what the mean ensemble of the models is telling us we're going to have. And then it also is showing us in this graph that we have a 60% probability, so likelihood, based on what the models are telling us, of having a percent increase change of 15%. Okay, so hopefully that's making sense to you all. So just to give you another case study on the North Fork Teanaway, we have all 10 models, so this is good news, are saying well, I guess in some senses, are saying that we're going to have an increase in bankful width. Our range is between 12 and 45%. We've got a mean of 24%, and again, we have a 60% probability of change greater than 15%. So we have some idea of how much magnitude change we see here. And this is just one hypothetical here, okay? Let's say we have a current bankful width. We've gone out to our creek in the Tucannon, and we've measured it at 8 feet. So the way we designed stream sim culverts, if you can recall that 1.2 times bankful 0.2, that would give us a culvert width design of 11.6%. So this is if we do it based on our current design metric. So what this would say is that 9 out of the 10 models are projecting that this culvert is actually going to be too narrow in the future. And 1 out of the 10 is actually saying that the bankful width is going to be greater than the culvert width, which is not good for fish passage and not good from a permitting point of view. So again, we can perhaps use our mean future bankful width, our projected increase, and design a culvert for stream sim with our future mean and get a bankful width of 13.7%. And that would put us well into the comfort zone as far as into the future for fish passage. So again, one possible way that managers might be able to use this information and determine what's going to be important and how much risk we're willing to take on. So again, this was kind of our first stab at incorporating climate change into our design process. We're looking into doing an economic analysis, which is really going to factor in culvert costs, as we can see if we're sizing our pipes. I mean, we already asked for pretty big pipes anyway, so we'll see how this works in the future. And we also want to build a model, a sediment transport model through culverts, and be able to look at just any range of scenarios with bed material type, slope. This is really my bread and butter, so I get excited thinking about it. And so those are the next steps. So let me know if you have money to fund this, because that's what us scientists do. And with that, I thank you. I really want to put out a special thanks to the North Pacific Landscape Conservation Cooperative who funded this project, and to our project team, a group of really amazing people. Okay.
So, is WDFW, for those of us that do these crossings, are you guys gonna put out recommendations for our areas of looking to the future of what, I mean, right now it is 1.2 or plus 2.
Mm-hmm.
Should we be designing for 1.5, just to be safe on, on our design, when we go to like surfboard for funding and, I mean, when you get to a certain size, the cost difference between a bridge and a culvert, yes, the bridge is still more expensive, but it will last longer in the long run. It's probably a better bang for the buck.
Go for the bridge. No, but as far as actually,
Are you recommending that we should go to 1.5?
I'm not recommending anything because I'm not a policymaker, but it is going to move forward. And again, that's kind of the risk component. I think it'd be really critical to look at where you are. I know you work in Pacific County, so these rain dominant basins may or may not have that percent increase in bankful width to where you are going to have to size up per se. But the hope is that if you have some indicator of what the percent increase is going to look like, you can at least do the math and see, okay, well, if I really was factoring in climate change and really wanted this pipe to last onwards for 100 years, here's what I would do. Here's what the projections are telling us, and here's how I could size it according to future predictions.
Yeah, because we're getting two really interesting phenomena with this climate change. One is that not only do we have to take into account for the larger amount of water flow, like our 14 inches in 48 hours, but it's the around the sides of the crossing where the road is, that is having much higher flow, and it's ripping out the sides. We had that at Nushka, Friend Creek.
Oh,
so
yeah, I know that project.
There's that situation. Then also we're seeing that with more rain flow where we're closer to the ocean, we're affected by tides. That, we're instead of going with the 100-year model, we're having to go with the 500-year, because when there's these heavy rain flows and the tides in, there's water can't go anywhere. So those lower areas are just really filling up.
Yeah. So I do want to say, we can talk later, but
sure.
we are in the midst of developing new guidelines for tidal crossings as well. So we're working on it.
Fantastic.
Okay. Yes.
Can I just make one slight amendment to that? So I'm also from Washington, part of Fish and Wildlife. I just want to be really clear that we're not right now changing our policy or practices. Right now, this is sort of our best science. We're testing it out with managers. We're going to do appropriate work with a lot of stakeholders. This is a can be very contentious issue for the agency. We want to make sure that our stakeholders are really ready and well briefed before we.
Sure, but I just
want to make sure that
I'm just naturally an overbuild kind of guy.
The letters start coming in next week. Jane and I are going to be in really hot water.
Yes. So you mentioned that, and so everything here was focused on the high flows. If you're adapting culverts for high flows, recognizing that no standards are being changed yet, but if, let's say you go to that and you start adapting these culverts for these higher flows, what is the potential that that ends up creating more problems on the opposite end for the low flows? So, does designing for higher flows also end up taking care of the low flows problem as well? Or does it depend? Like, could you get yourself into trouble?
Well, I think that it's important. So perhaps in Eastern Washington, where we do see lower projection, that the flows are actually going to be decreasing. It's important to keep in mind that we still have to design for today. I can't tell you that I've directly considered if a bigger pipe would have implications for lower flows. That's a very interesting question, and anyone.
But I think she's asking about summer flows, which are going to decrease, whereas flood flows in winter are going to increase in a lot of places. So if you have a bigger pipe, does that mean shallower water through the culvert in summer?
So I used to work at the King County DOT, and so with our culverts, we would put in a new culvert. We would put in stream bed gravel in it because we wanted a natural stream bed, so sometimes it would be a bottomless culvert. But one of the key things we had to do, because we were always making them wider, we didn't want to get that laminar flow over it, because you get the stream bed all even, and then the water would be really shallow, fish couldn't get through. So we would build natural structure within the culvert to maintain a low flow channel through the culvert. So you can put a boulder here and then a boulder here, and then that creates some sinuosity and creates a sort of natural scouring through the culvert to maintain a low flow channel. So it's critical to actually incorporate that in your stream bed design inside the culvert. Think about that.
That's a really good point. And DFW definitely does provide guidance on how to create a thalweg, and we definitely want that done within the pipe itself. Yes.
I have this is probably a naive question, but you said you were going to look at cost benefit, and at some point it seems like it might not be worthwhile to keep the road. Does that factor into the cost benefit?
It could.
Yeah.
We haven't gotten there yet, to be honest, but yes, I would say that that would factor into it. And you know, and again, a key thing that comes to my mind would be a culvert versus a bridge, for example, and the cost differences there. Okay, so I really want to leave up some time for us. Oh, but we don't have it. And we're done. But I hope that, you know, if you have questions or ideas for us, that you can stick, and that we'll be here for a little while longer at least, and can answer any more of your questions. And thank you very much for coming.